Okay, we're going to start with the do now. The first thing you're going to do is find f of 3, which again means you're plugging 3 everywhere you see x. So take a second to do that now. So you should have something that looks like this. 3 squared plus 2 times 3 minus 3, which is 9, plus 6, which is 15, minus 3 is 12. Your next thing is to find f of x plus h. So everywhere we see x, we are going to plug in x plus h instead. So you should have this written down. We're going to do this in stages. If you remember from a few weeks ago, when you have x plus h all squared, you'd have to expand it and FOIL, so x plus h times x plus h. This will give you x squared plus 2x h plus h squared. So this part in red is this part in red here. And then we would have to distribute the 2. So we have 2x plus 2h, and then minus 3. This is all there is to this part. We did this for a reason, because this is part of the difference quotient. So we're going to take a look at calculus phobe right now. Okay, let's go back to calculus phobe and the difference quotient. Okay, so this is lesson 1.
Before we get started, we need to answer one question. What is a derivative? Well, in calculus, the derivative is the slope of the tangent line to a graph. For instance, here's a graph, f of x. The point...
Excuse me.
Before we get started, we need to answer one question. What is a derivative? Well, in calculus, the derivative is the slope of the tangent line to a graph. For instance, here's a graph, f of x. The point C that I've noted. The tangent to f at x equals c would look like this. In essence, a tangent line is just a line that touches the graph once at that point. Sort of like a pencil resting there. Now, a function can have all sorts of different derivatives because, as you progress along a function, you can have all sorts of different tangent lines. Watch as the dot, which represents the x value, travels along the function, and how the tangent line changes as the dot moves. We need to figure out a way to determine exactly what the slope of that tangent line is, and we do that using something called the difference quotient. In this section, I'm going to show you exactly where the difference quotient comes from. Here's a graph called f, with a point on it labeled x. My goal will be to find the slope of the tangent line to f at that point. First things first, the coordinates of this point are x, comma f of x. Now, here's how I get my formula. I'm going to move a small distance to the right of x, and I'm going to call this small distance delta x. It's mathematical language for the change in x. Therefore, this new location is the total distance of x plus delta x from the origin. And this new point has coordinates x plus delta x, comma, f of x plus delta x. Now, if I draw the line that connects these 2 points in red, it's called a secant line. It's not exactly like the tangent line we're looking for that I'm showing in blue, but at least it's a start. I'm going to go ahead and try to find the slope of this secant line. And to do that, I'll use the old formula from algebra, where slope is equal to y2 minus y1 divided by x2 minus x1. And I'll get the slope is f of x plus delta x minus f of x, all divided by the quantity x plus delta x minus x. And if I subtract those x's in the denominator, I get this. Now remember, this is the slope of the secant line, not the tangent line. So I'm not done yet. I need to find a line which is closer to the tangent line than this one. Let's look at that graph again. What happens if I were to make delta x smaller? In other words, my second point will be closer to x than it was before. Now, if I draw the secant line connecting my original point to my new point, which is slightly closer, I will get a secant line which looks more like the tangent line than the previous one did. It's getting closer to it. In fact, the smaller delta x is, the closer this secant line will be to the tangent line. Watch on this animation as the delta x goes from really big to really small. The red secant line comes closer and closer to the blue tangent line. We want delta x to be as small as possible. So therefore I need to make a small adjustment to my secant slope. Remember, that was f of x plus delta x minus f of x all over delta x. But we want to specifically say that that delta x needs to be as small as possible so those lines basically overlap. And to do that, we'll use a limit. All we do is add in the limit as delta x goes to 0. In other words, I want delta x to become so small it's almost 0. It can't be 0 because then I would have 0 in the denominator of the fraction. That's why I have to use a limit. And I say get that delta x as small as possible. This is the difference quotient. It is the mathematical definition of the derivative.
Okay. So again, you could watch this video at home. Okay. So what we have here, again, this is what was in the video. I did say before I don't like using delta x because it could be confusing. So we are actually going to use this one here, f of x plus h, and then all over h. And what the h actually stands for is horizontal distance. So delta x just meant how much you're changing from regular x, so in the x direction. So h is the horizontal distance. And what this represents, this is f prime of x. This means the slope of the tangent line. It means the derivative of x. And we're going to continue. What can we say about each denominator? Well, when we plug in 0, we should get 0. When we plug in 0 here, we should get 0. And here, when we plug in c, we should get 0. We're going to talk about this more next week, and this is called the instantaneous rate of change, and that is what we'll be talking about probably Tuesday or Wednesday. So our first example here is finding f prime of x if f of x equals 3x plus 1. So we're going to follow this limit notation. So we would start off by finding the limit as h approaches 0, okay, of f of x plus h. So what that means is we're going to plug in x plus h everywhere we see x. So we will have 3 parentheses x plus h plus 1. Okay, because of the plus 1 that's right here. Then we have minus, and now we have just f of x. But you have to be careful when you have f of x. You have to put it in parentheses, especially if it is 2 terms or more. Okay, and then all of this is over h. So our next step is simply to distribute the 3. So we have 3x plus 3h plus 1. Distribute the negative here. We get negative 3x minus 1. And all of this is over h. So the fun part is to cross off. 3x will cross off with negative 3x. Positive 1 and negative 1 will cross off. So ultimately now we have the limit as h approaches 0 of 3h over h, yet the h's will now cross off. So these are gone. our derivative, f prime of x, is actually equal to 3. That means the slope of the tangent line will always be 3. And it makes sense because this is a graph of 3x plus 1, which is a line with a slope of 3. Okay? So our next piece is this. I'm going to cover this. We're going to find f prime of x, the derivative of f of x squared minus 3x plus 1 by using the difference quotient. So again, we're going to be plugging in x plus h in for x. So here and here. Okay, and so that is right here in red, x plus h squared minus 3 times x plus h plus 1. Don't forget that you're then subtracting all of f of x, which is minus x squared minus 3x plus 1, all over h. So our next step is simply to expand. X plus h again is x squared plus 2xh plus h squared. We're going to distribute this negative 3, and then here we're going to distribute the negative. So let's see what this should look like. So this first part here is in the red. This second part of distributing negative 3 is in black. The 1 stays the same, minus x squared plus 3x minus 1. Okay, again, the fun part is crossing off. So we have x squared and x squared. Hint, hint, all of this stuff on the right will cross off. 3x, negative 3x, negative 1, and positive 1. So, don't forget, we're actually finding the limit as h approaches 0. But what we're going to do now is we are actually going to factor out an h, because you could see an h here, an h here, and an h here. So if we factor out an h and put what's left over, which is 2x, then plus h minus 3. So if you distribute this h back to these 3 terms, you will have what I have pointed out with the arrows. So all of this is over h, which will then cross off the h's. We now have 2x plus h minus 3, and we are now finding the limit as h approaches 0. Well, if you notice, we no longer have h in the denominator. Our only h is right here. So basically this is going to go to 0. So what do we have left? We have 2x minus 3. 2x minus 3. Okay, so this should be the end of video part 1. I want you to then play part 2, which will go into the explanation of what this means graphically.